All right, so today the thing that I'm going to show you is the same thing that I showed you last time, which is how to solve a system of linear equations, except today we're going to do it without a graph. No graphing today. So the method I'm going to teach you is substitution, and substitution is useful in a couple of different scenarios. The main scenario in which substitution is useful is if your equations are not already in slope-intercept form. Some of the graphing equations that we did, the equations weren't in slope-intercept form and we put them in slope-intercept form. You can still do that with these problems. I could put, for example, this second equation, 3x plus y equals -9. I could subtract the 3x on both sides, so it would be in slope-intercept form and then graph it. Totally fine, but if I don't want to put it in slope-intercept form, or if it looks like it's going to be really difficult to put it in slope-intercept form, substitution is a good way to go. The second time substitution is really useful is if your answer is not a whole number. And when we talked about graphing, we looked at a couple of problems where the intersection of the two lines was not a whole number. And if the intersection is not a whole number, it can be very difficult to tell from graphing where the actual intersection is. That's another time when substitution would work out well for us. So refresh my memory, because it's been a long time since we've done this. What does the word substitution mean? Not even just in math, but in general, like life in general, the word substitution means what? Replacing something. For example, we were talking about making a cake earlier that does not use eggs, and one of the suggestions Ellie said was, well, why don't you just use egg substitute? Why is it called egg substitute? Because you use it in place of eggs. If your teacher is gone for the day, you get a substitute teacher, someone who replaces your teacher. Hopefully temporarily in my case, but nevertheless, someone who replaces your teacher. So solving equations by substitution means replacing one piece of an equation with something else. Okay, so let's take a look at these two equations that I wrote for you. And what I want you to notice right off the bat is that the first equation, the top one, is solved for y. It says y equals 2x plus 1. We see equal signs so often that it's easy to forget exactly what an equal sign means. An equal sign means these two things are the same. Y and 2x plus 1 are the same thing. That's what an equal sign is telling us. Y and 2x plus 1 are interchangeable because they are the same. So look at the second equation. The second equation has a similar problem to the first equation, which is that they both have two variables in them. They both have the variables x and y. It is not possible for me to tell you the value of a variable if the equation has two different variables in it. The top equation is already solved for y, it's y equals, but that does not help me at all in telling you the number that y equals. I also have no idea what number x equals. So an equation that has two variables in it is unsolvable by itself. But what if I were to go to that second equation, 3x plus y equals -9, and replace or substitute the y with 2x plus 1. The first equation tells us y and 2x plus 1 are the same thing. They are interchangeable. So let's use that. Let's take this second equation here. I'm going to do 3x plus, and in place of the y, I'm going to put 2x plus 1. And it equals -9. So I have just substituted right here between this step and this step. I substituted 2x plus 1. 2 minus 3 is -1. Why are you doing that? Shouldn't you be doing 2 plus 3? Anyway, we'll get to that in a second. Now look at this new equation that I wrote. 3x plus 2x plus 1 equals -9. The parentheses around the 2x plus 1 are not required in this problem, but I do want you to get into the habit of whenever you do substitution, putting the thing you substitute in parentheses. I really want you to get into the habit of doing that. It's not so that you do it first. It's so if instead of plus y, this had been times y, you make sure to multiply everything in the parentheses instead of just multiplying the first thing. So in this problem, it doesn't matter because it's a plus sign. But if instead of a plus sign, that had been a minus sign or a multiplication sign, the parentheses would make a big difference. So just get in the habit of always using parentheses when you substitute. That being said, I want you to look at this problem and tell me what was the advantage of doing that substitution? Because it looks like I made the problem way worse. Yes, ma'am. Because how many variables did I have in the original equation? 2. How many variables do I have now that I've substituted? 1. And I can solve an equation that only has 1 variable. So let's do that. First of all, as I said, we don't need the parentheses, so we can just go ahead and drop those. You can drop parentheses if it's addition. And then as Shelby pointed out, I can combine my variables together. I have a 3x and a 2x. When I combine those, what do I get? 5x plus 1 equals -9. Then what? So let's subtract 1 from both sides. Great idea. Very good. -9 minus 1 is -10. Correct as usual. Very good. Then we divide both sides by 5. -10 divided by -10 divided by 5 is -2. You are exactly right. I now know the value of x. X is equal to -2. The only thing left for me to do is to find the value of y. We replace the x. Now go back up and look at our 2 original equations. We had one, our first equation, that was already solved for y. Let's use that equation. Y equals 2x plus 1. But let's use this new piece of information we just discovered, which is that the value of x is -2. So I'm going to take this equation and replace the x with -2. Y equals -4 plus 1. Now you can see why parentheses are so important. Without the parentheses, that would look like 2 minus 2 instead of 2 times -2. So I end up with y equals -3. I'm going to recommend to you that you not leave your answers looking like this because our answer should actually be a coordinate. The answer to a system of equations is the coordinate that both lines go through. So I'm going to recommend you write that as -2, -3. The x comma y. So this is going to be our final answer. Final answer will be a coordinate. So that one seemed like it was fairly easy. Solving for x was the hard part. Once you solved it for x, just basic arithmetic left. But part of the reason that one was so easy is because one of our 2 equations was already solved for a variable. It was already y equals. It would have been just as good if that one had been x equals. What should we do if we're going to solve by substitution, but neither of our equations is already solved for a variable? If I was going to graph them, that's what I would do. But I don't want to graph them. I want to solve them by substitution. So what I really want to do is I need to take one of these two equations. It doesn't matter which one. And I need to do just enough algebra where the one of those equations is either x equals or y equals. Either x equals or y equals. So when you look at those two equations, x plus 2y equals 6 and 3x minus 4y equals 28, which of those two equations do you think is going to be easiest to get a variable by itself? I agree with you. I think the first equation is going to be easiest. Why do you think that the first equation is going to be the easiest one to get a variable by itself? No, it's not a trick at all. I'm thinking the first one's the easiest because the x has a coefficient of 1. It's already just plain old 1x, which means if I solve the first one for x, I won't have to divide. I can just subtract 2y on both sides, and I'm finished. So let's examine just this equation. X plus 2y equals 6. And I'm just going to go ahead and subtract 2y from both sides. Now, I could have solved either one of these equations for either one of these variables. But the reason I chose to solve the first one for x is just because it takes the least amount of work. I could have solved the first one for y, but then I would have had to divide by 2. I would have had negative x divided by 2, which is kind of yucky. I could have solved the bottom one for x, but then I would have had to divide 4 and 28 by 3 because it's 3x. Same thing with the y. I would have had to divide by negative 4. I would have gotten the right answer if I'd done those. I just would have had to deal with fractions to get the right answer. I don't hate fractions. Fractions are people too. But if I can avoid fractions, I'm going to. Kind of like green vegetables. Like, if somebody forces me to eat them, I will. But if I can avoid them and have pizza instead, I'm definitely going to. So now I've got this first one solved for x, which is pretty nice. That's the substitution that I'm going to do. Remember what the equal sign means. These two things are the same or are interchangeable. The x and the negative 2y plus 6. So what I'm going to do is I'm going to take the second equation, the one that I haven't used yet, this guy, and I am going to replace the x with negative 2y plus 6. Replace or substitute. So instead of 3 times x, I'm going to do 3 times negative 2y plus 6. And then the rest stays the same. Minus 4y equals 28. Now, at first glance, it looks like I have made this problem way, way, way worse. But although I have made the problem longer than it was, I have one variable exactly right. So let's go ahead and do our multiplication, our distributive property here. 3 times negative 2y, and 3 times 6. So that's going to be negative 6y plus 18 minus 4y equals 28. I could, if I wanted to move the 6y to the other side of the equals, but before I start moving things back and forth around the equal sign, I think the first thing I want to do is combine my like terms. You see some of those? Well, 28 and 18 are on opposite sides of the equals, but negative 4y and negative 6y are on the same side of the equals. So what's negative 4y minus 6y, or vice versa? Yes? Negative 6 plus negative 4 is very good, Brooke. Negative 10 plus 18 equals 28. Very good. 28 minus 18. So I'm going to subtract 18 on both sides. Excelente. So that's going to leave me with negative 10y equals 10. And then divide by negative 10. You got it. Negative 1, the number of dates I had in high school. Am I finished? I'll give you a hint. Do I know the entire coordinate? No, I only know half of it. I know y. And I found y by substituting in the second equation, 3x minus 4y equals 28. So the way I'm going to find x is by substituting into the first equation, x plus 2y equals 6. Or if I wanted to, I could also substitute into the equation after I did some moving around, which is this guy. The x equals negative 2y plus 6. I think that actually might be an easier equation for me to substitute into. Why? Why might that be a better one to substitute? Because I know y, and also because x is already isolated. Yep. So let's do some substitution. X equals negative 2 times negative 1 plus 6. So negative 2 times negative 1 is 2. And I don't have a calculator handy, so what is 2 plus 6? It's 8. 8, 8, 8 is great. You can hold it this way. You can hold it that way. It's still 8. 8, 8 is great. It makes me shout, hooray. I can count 8 skates sitting on a crate. 1, 2, 3, 4, 5, 6, 7, 8. Yes, I can really state that 8, 8, 8 is great. It's a song by one of the greatest mathematicians of all time, Count von Count. I got some Count fans in the chat. I mean, if you want somebody who knows their numbers, can't go wrong with that guy, Count von Count. And there's another one on Sesame Street, Countess von Backwards, I think, who also likes to count, but she counts down instead of up. He is a Muppet, but it's from Sesame Street. I believe the name of the type of puppet they use is called a Muppet. It is a monster puppet or Muppet. Brock says we have to wait till college to talk about Count von Count because he's advanced. You're probably right. All right. let me show you a weird one. I mean, a weird math problem. I think there's already enough weirdness in this lesson already, but let me show you some weird math. So there's one thing that I like a lot about this system of equations. What do you think I like the most? I do like the first one the most. How come? It's in slope-intercept form, but I don't really care about that because I'm not going to graph them. The thing I like the most about the first one is that there's already a variable isolated. It's already y equals, which is good. It means I'm already ready to do some substitution. Y and 2x minus 4 are the same thing. So I'm going to take my second equation. He's so pretty. And I'm going to replace the y in that second equation with 2x minus 4. So I'm going to do negative 6x plus 3 times 2x minus 4 equals negative 12. I actually substituted. It's true. Looks like I have a little bit of distributive property to do. The negative 6x will stay put. And then I'm going to have 3 times 2x, which is 6x. And then 3 times negative 4, which is negative 12, equals negative 12. Yep, it is. So whenever I start combining my like terms, the minus 6x and the plus 6x cancel out and leave me with 0. So then I have negative 12 equals negative oh, what happened? Oh, no. What's the dealio? My x's are gone. This is called an identity. When something is equal to itself, negative 12 equals negative 12. I hope I'm not blowing anybody's mind by telling you that negative 12 is in fact the same thing as negative 12. When you end up with something like this in a system of equations, negative 12 equals negative 12, what this means is our two equations were the same. That's what this means. Exactly. This means both equations are the same. And from yesterday, or I guess 2 days ago, we talked about what happens when both equations are the same. It means that if we were to graph this, it would be one line on top of the other, which provides us with infinite solutions. Now I can prove that by going back to these equations, and the first one was in slope-intercept form, y equals 2x minus 4. Let's take the second equation and put that one in slope-intercept form, just for funsies. I know, I think it's fun too. So add 6x to both sides. Just trying to get y isolated. As opposed to what my last girlfriend did, which was to isolate her x. Divide by 3, divide by 3, divide by 3, and I get y equals 2x minus 4. Lord have mercy, that looks familiar. It's the same as the first equation. So if I take the second equation and put it into slope-intercept form, it looks just like the first equation, which was in slope-intercept form. So if I graph these, I would have the line y equals 2x minus 4, and then right on top of it, y equals 2x minus 4. Can anybody take a guess what would happen if I were to have a system of equations that had no solutions? The x's would still disappear. What would happen though if I had no solutions? They wouldn't intersect at all. If I was graphing, it'd be two parallel lines. If it had no solutions, everything about this problem would be exactly the same, except the last step would be something like negative 6x plus 6x minus 12 equals minus 13. Now, when I combine these like terms, the x's, I end up with negative 12 equals negative 13, which is not an identity. That's what it looks like when the lines are parallel. And if the lines are parallel, what can you say about the solutions? We ain't got none. And that is everything you need to know about solving systems of equations by substitution. Does anyone have any questions?